let's take a look at magnetic fields. So your introduction to magnetic fields and magnets and magnetism is probably like a magnet on a fridge or a compass needle or something like that. You probably know that magnets have poles. We call them north poles and south poles. And like poles repel and opposite poles attract. So north pole attracts a south pole attracts a north pole, north repels north, south repels south. And just talking about it in that way, it seems pretty darn similar to electric charge, right? Like charges repel, opposite charges attract. But there are some pretty fundamental differences with magnets. If I draw the magnetic field around a bar magnet, you can start to see some of those differences. So the magnetic fields, and remember these are magnetic fields now, not electric fields. The magnetic field around a bar magnet looks something like this. So you can see, yeah, the magnetic field mostly goes away from the North Pole and mostly goes into the South Pole, but look inside the magnet. Inside the magnet, it's pretty darn different. And we're going to kind of see why that is a little bit later. One of the things that's really different about magnetic fields is their origin. Magnetic fields, it turns out, are created by moving charges. Now that seems a little bit odd, because now you're probably thinking to yourself, wait a minute, in a bar magnet, where are the moving charges? You pick up a bar magnet, or pick it up off of your refrigerator, you don't see anything moving inside of that magnet. So you're going to have to trust me for now. We'll get to that a little bit later. But really, to understand magnetism, we have to understand the magnetic field. So that's where we're going to start. The magnetic field is represented with the letter capital B. I don't know why, but it is. The unit of magnetic field is the Tesla, which is represented with a capital T. There's another unit called the Gauss, which is also common, and 1 Gauss is 10 to the minus 4 Tesla, so a Gauss is smaller than a Tesla. But we're going to use Tesla. That's the SI unit. Now, before we get any further, a little bit of background. If we have charge moving along a path, that's called a current. A current, which is usually represented with the letter capital I, again, don't know why, but it is. A current is the rate of charge flowing past a point. So the equation that's associated with that is that the current, I, is equal to delta Q over delta T, where delta Q is the charge that flows past a point, and delta T is the amount of time that it takes for the charge to flow past the point. And now we can kind of see what the unit of current would be. Current is delta Q over delta T. That's charge divided by time, so coulombs divided by seconds. So the unit of current is a coulomb per second. Turns out a coulomb per second is equal to an ampere, which is represented with a capital A. Now an ampere, if you remember, is one of the fundamental SI units. So here we're seeing it in practice. Now, for historical reasons, the current, the direction of the current, is defined to be the direction that positive charges flow, or opposite the direction that negative charges flow. So if we have a bunch of positive charge flowing to the right, all right, the current is to the right. And if we have a bunch of negative charges flowing to the right, in that situation, we say that the current is to the left. All right. Okay, but how does this get to the magnetic field? Well, I said that moving charge is the source of magnetic fields. So let's say that we have moving charge moving along a line. In other words, we have a current. And let's make the current flow to the right. So that means we either have positive charge flowing to the right or negative charge flowing to the left. To figure out the direction of the magnetic field around this moving charge, we use something called a right-hand rule. And for this situation, the right-hand rule goes like this. First part, take your right hand's thumb and point it in the direction of the current. Second thing, then imagine grasping the wire with the fingers of your right hand. It's a little hard to explain. It's probably easier to demonstrate in real space, and we'll do it in class. But yeah, you grasp the wire with the fingers of your right hand. The direction that your fingers move when you do that is the direction of the magnetic field around that wire. So if we try that, up above the current, the magnetic field would be out of the page. And in the region below the wire, the magnetic field would be into the page. Now, here I've written out the words out of the page and into the page. Turns out, in physics, we have a convenient way of writing that. If we have something coming out of the page, we draw that as a circle with a dot. And if we have something going into the page, we draw it as a circle with a cross. The reason why is we're trying to draw an arrow that's coming out of the page and into the page. An arrow coming out of the page towards you, well, you would see the tip of the arrow. So that's what that circle with a dot is supposed to look like. It looks like an arrow coming right at you. And if you have a circle with cross, you're seeing an arrow going away from you. So that's looking at the tail feathers of the arrow as it goes away from you. All right. Let's look at a different situation. Let's look at a line of current again, but now this time let's have the line of current coming straight at you. Have the line of current coming out of the page. In that situation, here's the current. Okay, current's coming out of you. Let's use that circle with a dot. That's what it represents. If we find the magnetic field at a bunch of different points around that, what we'll see is, let's see, well, up there, the magnetic field there, the magnetic field, a bunch of different points. So if we put that all together, if we have a current coming out of the page, the magnetic field lines look like this. And for reasons I'm not going to go into right now, the magnetic field is stronger when we're closer to the wire. So the magnetic field lines look like this. There, where the magnetic field lines are closer together, stronger field, and out here, where the magnetic field lines are further apart, we have a weaker field. All right, let's look at a different situation. Let's say we have a current loop, a loop of current going around like this. Well, what would the magnetic field look like around that current loop? Well, it's a little tough to do, but what we can do is we can look at a little segment of the wire up here at the top and try to figure out the magnetic field just caused by that. If we do that, inside of the loop, the magnetic field is coming out of the page, and outside of the loop, the magnetic field caused by that little tiny segment of wire is going into the page. And if we do that for all the little segments of wire all around the circle, the circumference of this loop, we would get that inside the loop, the magnetic field is coming out of the page, and everywhere outside of the loop, the magnetic field is going into the page. Now, if we had a loop of wire where the current was going in the opposite direction, we'd have the opposite magnetic field. Inside the loop, the magnetic field would be into the page. Outside the loop, the magnetic field would be out of the page. Now, if I draw this from a different angle, we can kind of see the three-dimensional nature of this. I'm going to try to draw it. I'm not the best drawing artist, but I'll do what I can. Here's a loop. I'm kind of looking at it in from an angle. Then, if the current's going around like that, here's the front, here's the back, the magnetic field lines kind of do this. They loop around like that. And if we had a bunch of loops, something like this, where the current's coming in and then it loops and loops and loops and loops and loops, and then it goes out. First of all, we call that a solenoid. And if the solenoid has current going around like that, the magnetic field would look something like this. Inside of the solenoid, the magnetic field would be in this direction, and outside, it would loop around like that. So that kind of brings us back to the bar magnet. The bar magnet had a field kind of similar to that solenoid. So if we go to this bar magnet, it turns out that a basic model of a bar magnet is we have all of these little atoms that make up the magnet. And all of these little atoms have their own little magnetic field. And the magnetic fields, this isn't exactly true, but it'll work for our purposes, the magnetic fields are caused because we have little electrons spinning around the atom. Now, if you've taken much more physics, you might start getting mad at me and you might start saying, hey, that's not true. There's some details that you're missing. Yeah, okay, I'm missing some details, but this works for now. So all these little atoms, or all these little electrons in the atoms are whirring around in a circle. All these little electrons are tiny little current loops. And all these current loops are creating tiny little magnetic fields. And in a bar magnet, all of those little magnetic fields are aligned to create a big magnetic field. And it creates a large magnetic field that looks like this. All right. Now I also want to point out, notice that the magnetic field lines are loops. They don't start or end anywhere, which is different than the electric field. Now we're going to see a lot of other differences between electric and magnetic fields, so this is really just the first of many.